So today's topics we want to cover the understanding air-operated double diaphragm pump basics, commonly referred to as AODD. So we're going to understand how to read an AODD pump flow curve, considerations for selecting the right pump, and examples of AODD pump applications. So let's go ahead and get into it. Understanding AODD pump basics. Well, back in 1955, there was no AODD pump. Our founder, Jim Wilden, was working at a steel mill out in Fontana, Kaiser Steel, and he was working in the shop where it would constantly get flooded out with ore and muck and a bunch of stuff. So Jim Wilden told his fellow staff members, guys, if I designed a pump that would pump all this muck out of here, would you guys buy it from me? They looked at him and told him, Slim, if you could design a pump that would do that, we think everybody would buy it from you. And lo and behold, an industry was born. So let's take a look at this video about understanding AODD pump basics.
This is a Wilden air-operated double diaphragm pump. How does it work? The liquid chambers are alternately filled and emptied by fluid that is drawn through a common inlet and discharged through a single outlet. The diaphragms in each chamber are linked by a single shaft, allowing them to move in unison. The air valve directs pressurized air to the back of diaphragm A. This begins chamber B's suction stroke, which starts as diaphragm B has moved toward the center of the pump, thereby creating a vacuum in chamber B. Atmospheric pressure then forces fluid into chamber B past the inlet ball valve. When the pressurized diaphragm A reaches the limit of its discharge stroke, the air valve redirects pressurized air to the back of diaphragm B. This begins the discharge stroke of chamber B. The hydraulic forces developed inside of chamber B force the inlet ball onto its seat and the discharge ball off its seat. This condition allows fluid to flow through the pump discharge. The same process occurs in the opposite chamber, constituting one full cycle. The pump will continue to run until inlet air supply is interrupted or discharge pressure rises to equal that of the air inlet pressure.
So simple enough. When you think of a diaphragm pump, think of a bathroom plunger, right? You got a shaft connected to a plunger. As it pulls or pushes product in and out of the toilet, that's what it's doing with the pumping media. It's basically drawing it in, drawing it out. So some of the advantages that we have over the competition is that we are great with shear sensitivity. Our pumps are dry run capable, meaning that you can run the pump dry without doing any kind of damage to shaft seals. All you're doing is you're putting unnecessary cycles on a diaphragm. As far as solids passage, we have anywhere up to 3-inch solids passage with our Brahma pumps. So meaning that you can get 3-inch size solids to go into the pump and come out of the pump. Maintenance costs are relatively low because all you're doing is replacing diaphragms and valve balls. The pump is also submersible. So if you can't pull the product out of a vessel, or if it's too much inlet pressure, you can always drop the pump inside of the tank and pump it from the inside out. Uh, it's intrinsically safe, and as long as you have the pump properly grounded, you can even submerge it in a flammable application. So you see other technologies out there. They do have good ratings in some areas, but not across the board where they'll get straight A's. That's where the diaphragm pump really excels. So as we start looking at the diaphragm pump, we think, well, why not standardize on this pump across the board? Well, there are limitations, right? So plastic models made of polypropylene and PVDF can handle products only up to 225 degrees Fahrenheit. So if you need anything higher temperature than that, then our plastic pumps will not work. We do offer metal pumps in aluminum, ductile iron, and stainless steel, and they can handle products up to 350 degrees Fahrenheit. Now, the metal can go higher, but our limiting factor is going to be our diaphragms, and our diaphragms have a maximum temperature of 350 degrees Fahrenheit. So anything higher than that, you would have to go to a different pump technology. Maximum flow rates, we can get up to 300 gallons. So anything over 300 gallons, you'd have to look into another pump technology. And as far as maximum fluid pressure, we can handle pressures up to 300 psi with our high pressure series. So availability and cost of compressed air is slightly higher than running just a electrically driven pump. However, in many instances, you can't have electricity and water mixed together. This is where the diaphragm pumps really excel in those areas. Our pumps do put out a pulsing flow because of the reciprocating motion of those pumps. Now we can mitigate that pulsation by using an inline or a integrated surge dampener onto the pump. So we do have a pulsing flow, but with using a pulsation dampener, that flow can be more of a laminar flow, and you can use these more on the process side for process style pumps. And another thing is inlet pressure. So our pumps can only see up to 10 psi of positive inlet fluid pressure. Anything greater than that, it impacts performance, and it also degrades the diaphragm life. So you want to make sure you keep your inlet pressure to 10 psi or lower to get the maximum efficiency out of a diaphragm pump. So those are our limitations on air-operated diaphragm pumps. And you understand how the pump works. It's got the 4 valve balls in each of the 4 quadrants, and it works with the diaphragm membrane pushing that product in and out. So why is that important on the diaphragm pump? Well, if you're pumping something like, say, a yogurt with fruit on the bottom, you want to keep those yogurt, the fruit intact in that yogurt so that it comes out tasting and feeling like fruit. If you're using a diaphragm pump in the wine industry, you don't want the peelings or the grapes to go through a gear and get mashed and change the flavor profile of it. So this is why people look at a diaphragm pump, because whatever the product comes into the pump as, it also leaves the pump as that same product with very minimal shear. Only when the ball is coming down on the seat will it change that product being pumped. So easy enough on the understanding on the basic workings of a diaphragm pump, right? Nothing has really changed on that pump since 1955 when Jim invented it, other than ways to make the pump more efficient or use less air to get the maximized gallons per minute. So the next topic is going to be talking about gallons per minute and how do we read an air-operated diaphragm pump curve. So he's looking like he's wondering what this all means. So what is he looking at? He's looking at a flow curve. There's a bar. There's bars, there's lines, there's dots, there's numbers, and it's all pretty confusing. But once you break it down and strip everything away, it makes it pretty simple. So what we're going to do is we're going to strip away all this stuff and we're going to take a look at it and understand how to read a flow curve. We're going to go through and see what each of the lines represent and understand them. So let's go ahead and get into that next. So we're going to start off with the blank canvas, right? No lines, no nothing, just a blank canvas. So in the left vertical rows, you see bar, which is going to be pressure, feet, which is going to be your head, and PSIG, which is going to be your air pressure. So as we start drawing the flow curves, you'll see the lines are going to start swooping, right? So let's see if we can. So as they swoop down, for instance, this 80 psi here, it's on the 80 psi line, and at 0 head pressure, you would follow that line all the way down to where it intersects the 0 psi head pressure, and your anticipated flow rate is going to be about 160 gallons per minute. If you were at 40, you would follow that line all the way down, and you're going to be somewhere between the 100 and 120, so we would call that about 110 GPM. So that's how you would understand the flow curves, the lines that sweep from the y-axis and come down and touch the x-axis. So the next line we're going to get into is going to be our air consumption. So we publish our data in scheduled cubic feet per minute, and these are the lines that swoop upwards from the x-axis and come up through the y. So where they intersect your head pressure, that is going to be where your line is going to land on, right? So we're going to step into these and see what it all means. We also add all of the graphs here so to help you easily identify one of your data points in the flow curve. So when you see all that put together, it makes a little bit more sense now. So what we're going to do is we're going to go into the definitions of the axes, right? So the y-axis, it represents the pump inlet pressure, and it also represents the head pressure. Now we show it in either bar or feet, and you can also use the PSI if you know what that PSI of head pressure is. So the line touching the axis is the air. The line touching the y-axis is going to be your your inlet air pressure, and then the x-axis is going to be your head pressure. Right. So now that we understand the axes, we'll go ahead and look at an example here. So where the air pressure and head pressure intersect, we know that as a duty point. So in this example, if we had 60 psi of air pressure here, and the duty point is here, we have to ask ourselves, okay, well, what is the head pressure? So you draw the horizontal line going across, and you'll see that it intersects with the 100 feet of head pressure. So 60 psi of inlet air pressure, 100 psi of head pressure gives us our duty point. So what is our flow rate? Because it's not going to go all the way out to the end of the curve. Where it intersects, you draw a line straight down, and that's going to give you your flow rate. So this one, it's not quite 60, so we would interpolate and call it about 58 gallons per minute. So this is where the SCFM comes into play. Now that you know your expected flow rate, your inlet air pressure, and your head pressure, now we need to determine what is going to be our SCFM, or our air usage. So you'll see here in this curve, it's right in between the 20 and the 40. So we would draw an imaginary line and interpolate that it's going to be 30 SCFM of air usage. So you can see there's endless possibilities, and the lines, all the bars that we put on there are just going to be there to help you and assist you to estimate your data point. Right. So we recommend running the pump to about 60% of the capacity. We call that the sweet spot. That's where you're going to get your best efficiency for running your pump. Not saying you can't run it out, right? This is just your best efficiency area here. So let's say if you're running 100 psi versus 10 psi head pressure, you can still run your pump there all day long. It's not going to hurt the pump. You're going to cycle that pump a lot faster, and the faster you cycle your pump means the faster you're going to wear out your internal components, your seals, your valve balls, and your diaphragms. So if you have to take a pump and you have to run that pump as far out to the right as you can, it's a good idea to go to the next bigger size pump and run the bigger pump slower to get you back into your sweet spot. Now, sometimes you're already maxed out, you have the biggest size pump there is, and you're still running out here on the far end. Well, that's okay. You can still do that. All it's going to do is you're going to just wear out some parts faster. So we recommend keeping your sweet spot right around this portion of the curve here. So now we're going to get into some actual examples here, right? So these are stuff that we'll get from a customer. They give us an example of some duty points here. So if we're looking, the example given is 103 gallons per minute. So we know that's what the flow rate is. That's what they need. And their system pressure has 30 psi of head. So we draw the line straight across from 30, and where it intersects the 103 is going to be our duty point. So you see right where that red dot lands is going to be right on the line of 80 SCFM, right? And it's also going to be right on the line of 80 psi. So by them giving us the gallons per minute desired and the head pressure to overcome, we would let them know what they need to run their pump at as far as inlet air pressure and what their air consumption is going to be. So 80 psi of inlet air pressure, and you're going to need 77 SCFM. Now, to determine what size compressor you need, it takes about one horsepower of compressor power would generate 4.5 SCFM. So if we took that 77 SCFM and divided that by 4.5, that's how you would size your compressor. So with that, you would need basically a 17 horsepower compressor, or you'd run a 25 horsepower compressor would give you your amount of air needed to run this pump at this duty point. If you had only a 15 horsepower compressor, you're going to fall short and you're not going to get your expected flow rate. So it's very important when you're sizing these up to make sure you have a compressor that can run that pump at those parameters, right? So the next question here, customer given is 100 psi of inlet air versus 50 GPM of head pressure, or 50 gallons per minute of flow rate. I'm sorry. So 100 psi inlet air pressure, 50 GPM. So where those intersect, we know that that's the duty point. So what we need to do is determine what is the air consumption and what's the head pressure going to be. Well, we can see it's not quite on the 60, so we'll call that 57. So our estimated air is 57 SCFM, and our head pressure, when we draw our horizontal line across, is going to be right on the 80 PSI line. So a lot of times customers don't have gauges, but they do know how much flow they need, and they know how much air pressure they have in the plant. So this is where it's very important to understand how to read a curve so that we're sizing the correct pump for that application. Okay, so we're getting right into this now. Let's go ahead and get into a little bit of interaction here. We're going to do a poll, and we're going to see if you guys are following along and if we can understand what we've been learning here. So at this duty point, let's take a look. At this duty point, these are the 4 questions that we are asking. What is the inlet air pressure? What is the flow rate? What is the air consumption being used? And what is the head pressure? So we'll give you guys a little bit of time to go through these poll questions. And we'll see what you what everyone came up with. And those of you in the industry will know that everybody's flow curves are a little bit different, from gear pump to centrifugal pump to diaphragm pump. And everybody thinks that theirs are the easiest to read, but I can tell you that ours are the easiest to read.
Okay, Andy, it looks like for the first question for inlet air pressure, 75% of people said 60 PSIG.
All right, let's take a gander and see what the results are. 60 PSIG, that's where we're at. Our 60 PSI of inlet air pressure. How about flow rate?
All right, we'll give you about 30 seconds to ask answer for flow rate. Okay, Andy, it looks like 92% of attendees said 40 GPM.
40 GPM it is. And the air consumption. What about air consumption at this duty point?
All right, you should be getting that question now. We'll give everybody about a minute to answer. Okay, it looks like 84% of attendees said 30.
All right, so when we look at that, it looks like Yep, we split the uprights and we're going right at 30, right at 30 SCFM. So that just leaves us, the last question is, what is our expected head pressure at this duty point?
Okay, great. The poll should be showing up now. We'll give everybody a minute to answer. Okay, it looks like 77%, 78% of attendees said 50.
And 50 psi, right on the nose. So it looks like everybody's understanding how to read that flow curve, and you'll see that everywhere on this flow curve that is under the 120 psi air pressure is achievable with this pump. So anything on the outside of this flow curve is going to be, you'd have to go to a bigger size pump or size up to get to those parameters. So now we got the basics of how to read a flow curve. So we get this question asked quite a bit is, well, now that we have this data, we're pumping a viscous product, right? The viscous product in this example is going to be 35,000 standard Saybolt units. So what do we do there? How do we accommodate the more viscous product? So we know that the inlet air pressure needed for this one is 57 psi. The flow rate is going to be 40 GPM. The air consumption was 30, and the head pressure is 50. But this is all based on just standard fluid, non-viscous. Now, when you get to the viscous product, the 35,000 SSUs changes the results. So let's step into that and figure out how we do that. Right, so 35,000 SSUs, we find that on the viscosity correction chart, and these are all posted up on our public website under guides. You'll find the viscosity correction chart. At 35,000 SSUs, you'll notice there's a viscosity correction number there, which is 2.0. So if the customer needed 40 GPM, we would need to multiply that 40 times the correction factor number. So now instead of the customer needing 40 gallons per minute, the pump is going to need to perform at 80 gallons a minute to get that 40 GPM of the more viscous product. So that's how we adjust for the viscosity. So now that we know that, we take our 40, multiply that by 2, right? So you see how it moves everything further out. So it's going to now require additional inlet air pressure. The head pressure is going to stay the same because that's constant, but we have to adjust for the air pressure. So now, instead of the pump running at 57 psi, the pump has to run at 82 psi because it thinks that it needs 80 GPM to get that. And then also the SCFM is going to change because it moved further out. So now we have to come here and determine that the SCFM is going to be 70. So that's how we do it for viscosity correction. Now, if it was 3.0 viscosity correction, say if it was 70,000 SSUs, that would put it too far out, right? You would have to get somewhere about 120. It puts it on the outside of that curve. Therefore, this pump would not work for that application. You'd have to go to the next larger size pump. And that's how we accommodate the viscosity for diaphragm pumps, which is really nice. You don't have to buy all these extra units, variable speed drives, and transmissions and gear reducers. You just simply adjust the air up or down. And same pump out of the box works in most applications. All right, easy enough. We're ready for the next topic. So considerations for selecting the right pump. Now we know how the pump works. Now we know how to get the correct flow curve. Now, what about selecting the right pump? So currently, Wilden offers two styles of pumps, right? We have clamped pumps and bolted pumps. In this slide, you'll see this is a 2-in-1. The everything on the right half is going to be our original clamp series style pump, and everything on the left half of the pump is going to be our bolted design. So they share a lot of the same components, same diaphragm, same shaft, same pistons, inner pistons, outer pistons, But the bolted has a better design when it comes to containment. So back in 1955, when it was just a basic utilitarian pump dewatering, muck and wastewater, clamps would suffice. Now it's beginning to be more of a process pump, and people want to keep that fluid contained. So what we did is we created a bolted wetted path that's going to have far superior containment. In many cases, you're going to get an increased flow rate and a better overall design. And we try to keep the price the same price as the clamped band, and we kept the dimensions dimensionally interchangeable, so you can take that new bolted pump, drop it right into that clamped application, and it'll fit right in there. Hence, the name of the pump is the fit. So we got bolted versus clamped. The bolted pump is going to give you superior containment, increased flow, easier to assemble. If anybody's ever done any maintenance on the diaphragm pump, the clamps are the hardest to get on. Well, the bolteds remedy that by making it easier to assemble. And if we can keep the same price point, in many cases we can, it's a win-win situation. You get a bolted design, superior containment, increased flow for the same price point, right? So let's get into our offering. So our pump designs, we know we have two configurations, clamped or bolted. And as far as chemical compatibility, that's what's going to dictate which material we use. So currently we offer 5 different offers, or 5 different materials for our material offering, right? 2 in plastic, polypropylene being the entry level, PVDF being our higher grade plastic for more aggressive chemicals. Right? And then in metal, we have our entry-level metal being aluminum, ductile iron being a slightly more expensive, but a lot better for abrasion resistance, and stainless steel being our best material offering. So those are our 3 basic materials that we offer in metal. Then the plastic is poly and PVDF. Now for piping sizes, we offer our breadth and range is 1/4 inch all the way up to 4 inch. And you can see if you need 10 gallons per minute, the 1/4 inch pump can only go up to 6, so you'd have to go up to the next size pump, the 1/2 inch, which would get up to 16 GPM. And you would size it accordingly based on the port size of the pump, and then you would select your material offering as far as whatever's compatible. So as far as Wilden, we offer the largest breadth and range. It's a blessing and a curse because we offer the biggest variety. So it makes it a little bit harder for selecting the right pump. We have a really great online choice program that'll help walk you through it. You select the material that you want to pump, your desired flow rate, and your pressure, and the system spits out the recommended pump for you, which makes it really nice. Now, as far as air quality, some plants out there don't have the best air quality. ProFlow Shift is our flagship air distribution system for the best efficiency out there in the market. It's patented technology, uses the least amount of air, so it's doing its part out there to try to reduce that carbon footprint and use the least amount of air. ProFlow is our air distribution system for general process applications. It's been around since 1997, and it's got a large install base out there in the market. One of the caveats on ProFlow is that it's only available with the plastic air distribution system. So if you're pumping anything flammable and need to ground that pump, ProFlow is not the right choice for you. You would have to go to the ProFlow Shift. TurboFlow was our basic utilitarian pump for dirty air applications, tried and true. It's been around since 1955. And that's our entry-level air distribution system. That's used when you have nasty, dirty, wet air. TurboFlow is the pump for you. When we get into our diaphragm materials, this is where it gets the complexity starts, because we offer 9 different material options. Really only 3 styles though: rubber, thermoplastic elastomer, also known as TPE, or PTFE. And again, the material being pumped is going to dictate which diaphragm material you choose. For the rubbers, our entry level is neoprene, and then we jump into Buna. EPDM is going to be for higher temperature applications, and FKM is going to be our most expensive and least flex life because of the carbon that's in that diaphragm. But it does go to the highest temperature rating at 350 degrees Fahrenheit. Thermoplastics is our man-made elastomers that are injection molded. We've got 4 different material offerings there. Geolast is our TPE version of Buna. Polyurethane is our standalone poly diaphragms, good for abrasion and just general diaphragms. Hytrel is used in our FTA and abrasive and oil applications. And Santoprene is our, we trade name it as Wilflex. That is our best thermoplastic elastomer diaphragm out there for pumping anything that is going to be abrasive. So if you want the longest life out there, you go with the Santoprene, and that's going to it's going to have a lot of the same chemical properties as PTFE, but a fraction of the cost. Think of it as a low-cost alternative to PTFE. And then finally, our PTFE, which is a PTFE overlay, which requires a backup diaphragm. So basically, you would select a backup diaphragm that's also compatible, but the overlay on that diaphragm is going to be made of PTFE. And those are for the applications where whatever's being pumped is very aggressive or proprietary, and you don't know what the materials of construction or the materials being pumped are. You would select PTFE. Right, so now we're going to get into the examples of air-operated diaphragm pump applications. So basically, any fluid that can pour, can be pumped, right? So that's why people like the diaphragm pumps, is you can pump anything that's thinner than water, such as solvents, and anything that's, up to 90% slurries. So what we say is anything from mud to blood and everything in between can be pumped with the diaphragm pump, right? And we're not limited to just fluid. AODD pumps also can be used for powders. So if you have any powder applications out there, fumed silica, there are a couple caveats for pumping powder. 3 rules. The powder must weigh less than 25 pounds per cubic yard. The powder must remain fluidized. So you have to keep that powder aerated inside the pump. And the powder cannot clump when you squeeze it in the palm of your hand, because if it clumps, it's going to pack out and you're going to start seeing some shaft damages. But there are a lot of people out there in the industry that are using diaphragm pumps to pump powders, and they do it very effectively, especially pumping carbon black and stuff like that. So when we get into our typical applications of a diaphragm pump, right, you'll see that we're big in the chemical industry, paints and coatings. They pretty much standardized on our aluminum Santoprene pumps for all the major paint industries out there, our major paint companies out there in the industry. Mining, we are all over the mine fields out there, pumping diamond mines, coal mines. We have the largest solids passage out there besides the hose pump for the mining industry. Oil and gas, we are huge in that industry here in the U.S. and Canada as well. Water and wastewater, any of these applications you see here, the diaphragm pump does really good. In the next slide, we'll kind of go into more of where they're used at. Pharmaceutical, we have a whole line of hygienic series pumps for food and beverage and hygienic. So either products that are going on the body, in the body, or just topical creams, right? We have we're big in those industries for pumping pigments, fragrances, anything that they don't want damaged, right? Because of that sheer sensitivity, they don't want any of that stuff going through a gear pump or centrifugal pump, right? So when we look at the chemical industry, we're good in all these, acid transfer polymers, low solvent coatings, dosing. Paints and coatings, we have these patented diaphragms we call ChemFuse. They have no outer piston, so there's no outer piston abrasion. Diaphragms are the longest lasting diaphragms on the market, and they're patented technology. Good for pumping titanium dioxide based paints, which pretty much all the paints are going to nowadays. They were eating through diaphragms every 6 months. They use the new ChemFuse patented diaphragms, and they're lasting 10 times what they used to last before. They're also used in resin, solvents, filtration. So all that stuff leads to a diaphragm pump being a good application in paints and coatings. Like I said, in the mining, because we do have our Stallion pumps and our Brahma pumps, which have up to 3-inch solids capability, they use those for dewatering the mines and getting all those the sand gravel, pea gravel, and big chunks out of the mines out there. Now, when we also start looking into oil and gas, they're used out there for skimmer pumps. They just, they float them for any kind of spills. So we got crude oil, waste transfer, lube oil, glycol feed, emergency dewatering. So any time that there's like a Jiffy Lube and they need the pumps for pumping out of the drums into the vehicles, you can use our diaphragm pumps there. Most of the times, if you go to a Jiffy Lube, you'll hear all those pumps running in the background. So they're pulling all the bulk fluids out of the 55-gallon drums and topping off the vehicles. Right, water and wastewater, we're huge in that industry. We have a largest pump in the industry with a 4-inch diaphragm pump that's big in the water and wastewater industry. It uses a 5-inch ball valve with easy access to the balls. So if there's any kind of sludge or any kind of waste that gets stuck in there, they can easily take that lid off without pulling the pump out of service, and they can quickly dislodge whatever's stuck in the line and get that pump up and going again. Those are huge in the sewer treatment facility for bilge pumps on ships and just cargo tankers. They use those all over. And that's kind of the gist of our diaphragm pumps, right? So more and more, we're starting to see these get into the process, the chemical process, mold filling, ceramic slip. And the diaphragm pump is good because they don't run as fast as some of the other pumps. So the faster those pumps work, the faster they wear the parts out. So diaphragm pump cycle's pretty slow, so we're able to get some really, really good life out of the diaphragm pumps in the ceramic industry. Semiconductor, they're good for the acid etching waste benches, for making the solar panels, semiconductors, it's all that stuff there. Food and beverage, we have pumps that start off at the FDA level for pumping high acids, ketchups and high vinegars for hot sauce, all the way up to high-end, high purity food and beverage that are used for milk and dairy production, whether it needs to be CIP-able, SIP-able, so clean in place, steam in place, and we have some patented technology on those hygienic pumps as well. So it's a good overall, well-rounded pump that goes into any market out there. So what we're trying to do is just educate people out there on the better uses of diaphragm pumps. And if you got a tough application, give us a holler, and we can definitely help you out with your application and see where a diaphragm pump can work for you.